Ndeyo yatandike
ate okola live mbadde tuliko. Warahmatullahi wabarakatuh. Mr. Chitandwe is your host today. We are going to handle AC circuits. Previously, we are talking about alternating current through a pure capacitor. And we said that apparently AC flow through a capacitor while DC does not. The reason is that direct current capacitance charge Q is given by CV. So that means when you connect a capacitor to a direct current source, the voltage increases until it is fully charged. Once it is charged, current flow stops. Whereas with alternating current, as the voltage is increasing, the capacitor charges, and when the voltage is decreasing, the capacitor discharges. Meaning that charging and discharging occurs simultaneously, leading to continuous flow of charge, and therefore the rate of flow of charge will indicate that there is flow of current. Now, we're interested in deriving the expression for the relationship between current and voltage. We say that if this is our circuit, in which the supply voltage is V0 sine Wt, and then connected to a capacitor of capacitance C. We say that we are interested in getting an expression for the instantaneous charge Q is going to be given by CV, which is the same as CV0 sine Wt. Now there is a relationship between current and charge. From the definition of current, instantaneous current is going to be the rate of flow of charge. Current I is going to be the rate of flow of charge, dq by dt, which is going to be the same as d by dt into CV0 sine Wt. Our interest is to get the value of the current. So we are differentiating with respect to t. So I instantaneous is now going to be equal to CV0, these are constants. You first differentiate the angle, W, then differentiate the ratio. When you differentiate the side, you get a cos. So we have a cos Wt. Now in the end, we are noting that current I is now going to be equal to I0 cos of Wt. In comparison with this derived equation, we end up getting I0, which is the peak value of current, to be equal to CV0 W. Now, the original expression for voltage was V0 sine Wt, and the current that is corresponding with the voltage in our capacitor is going to be I0 cos Wt. Now, for easier comparison, we can convert the cos in terms of sine, and then we say therefore I is equal to I0 sine Wt plus pi over 2. This expression could be got from our trigonometry. You know, from trigonometry, sine A plus B is the same as sine A cos B plus cos B plus sine B cos A. So if we relate it to this one, we are now going to note that sine term A is WT plus B is pi over 2, which is the same as sine A, which is sine WT, cos B, which is cos pi over 2, plus sine B, which is sine pi over 2, cos A is cos WT. Now we end up realizing that cos pi over 2, which is cos of 90, is 0. So the whole of this one turns out to be 0. Plus sine pi over 2 sine 90 is 1. And therefore the expression remains cos WT. So that means we end up realizing that cos WT is the same as sine WT. So that is the reason why here, instead of having cos WT, we have replaced it by sine WT plus pi over 2. So that one will mean, if we make a clear comparison between this equation and then this first equation, we end up realizing that the current is leading voltage by pi over 2. Because these expressions are tallying, the only difference is pi over 2. So conclude that therefore, in a capacitor, current leads voltage by first term pi over 2. Or you can say, or voltage lags current by pi over 2. Voltage lags current by pi over 2. So that is the relationship between voltage and current in a capacitor. Now, we have what we call variation of voltage in terms of graph, variation of current and voltage in a capacitor. In a capacitor. So here we are going to express it in terms of graph. This is voltage and current, and then this is time element. Since the voltage is a sinusoidal voltage, therefore a curve is going to be a sine curve for voltage. We will indicate this one to be for voltage, this is V0 sine WT. Now, since we said when the voltage is 0, current is maximum, linked by pi over 2, so the current will begin from here. We can use the dotted line, such that when the voltage is maximum, current is 0, and then this one can extend like this. So this is the expression for current, which is I equal to I naught cos WT, or you can say sine WT. So the variation of current and voltage So if you are told to draw a graph to show the variation of current and voltage, that is the graph you draw. But sometimes we may be told to draw if the, in terms of phase relationship, the phase relationship is going to be that current is going to be leading voltage by pi over 2. So here the angle is pi over 2. If you are to draw it graphically in terms of voltage and current, it is going to be expressed like that. Then there is what we call reactance. There is what we call reactance. We said reactance is the non-resistive opposition to the flow of current in either an inductor or a capacitor. Now, if it is specifically for a capacitor, there is what we call capacitive reactance. Capacitive reactance. So capacitive reactance, we say, is the non-resistive opposition to the flow of alternating current in a capacitor. Non-resistive opposition to the flow of alternating current in a capacitor, as we see it there. And it is denoted by the letter XC. And XC is the same as 1 over 2 pi FC. Or you can write it as 1 over WC, for that matter. Now, we may want to prove that expression. We may be interested in proving the relationship between capacitive reactance and that one. So we say we're now going to realize that the content is almost the same. From here, CV is equal to CV naught sine WT. Instantaneous current I is going to be dq by dt, then which gives cos of WT. Then current I is given by that, such that I naught is equal to CV naught WT. Now here, that's where the change comes in. Down. Now we go, reactance is generally resistance, is compared to resistance. So resistance from Ohm's law is given by IR, therefore R is equal to V over I. So if you just substitute where there is resistance and put reactance, it is simply say XC is equal to V over I. Or it could be written as VRMS over IRMS, or V naught over I naught. So from the definition, we are going to have capacitive reactance XC is now going to be equal to V naught over I naught. But already from this expression, we have noted that CV naught is compared to I naught, and it's the same as I naught CV naught, which is now going to be written as V naught over I naught, which is CV naught W, and that one, this one is cancelled, and we remain with 1 over WC or CW. But W is given by 2 pi f, so implying that XC will be given as 1 over 2 pi FC. And that is the expression which we are yearning to get from the graph. Now, we may be interested in in answering some questions that we left previously. There are questions we left in the other previous time. We handled number 1 and number 2. Number 3, we did not exhaustively handle it. So I want us to look at number 3 with some degree of detail so that we are able to relate to what we want to handle today. We talked about number 3 was saying, define why is alternating current referred to as sinusoidal. We said because its variation with the time varies as a sinusoidal. Its time dependence varies as a sine curve, as we noted. So we said the variation of its value with the time is a sine function. We also said, according to part B of the question, we are meant to have, that is number 2. Number 3, we're having a current, derive an expression for the average power dissipated in a resistor. That one we already have in our notes. Then we have current I was given as sine 2 pi f. We say current I was given as I naught sine 2 pi ft. You remember in a capacitor we had begun with voltage. This time round we have begun with current. So in other words, you want to take this one back to that one. So the question is saying that derive the expression for the PD across the capacitor. Now here we are aware that we begin with instantaneous charge. Charge Q is equal to CV not instantaneous charge is CV, and then instantaneous current I is equal by dq by dt. So, but our current I is given by this, so we are going to have I naught sine 2 pi ft equal to dq by dt, which dq by dt is the same as CV. So you can simply replace where there is dq by t, but we replace it by CV. So implying that this CV is equal to I naught sine 2 pi ft dt. We look at that one. So we want to get full, we integrate either side. So here we remain, we integrate CV, we get CV. Here we get I naught sine 2 pi ft dt. Now here, you need to be careful with the integration of this kind of the sine Wt. We are going to be integrating using the mathematical principle that the integration is the reverse of differentiation. You recall that this is a side work a bit. That d by dt, when you differentiate d by dt, when you differentiate the cos, for example, 2 pi ft, we'll be getting negative sign. We first differentiate the angle, so it's going to be 2 pi f. Then we differentiate the ratio. When you differentiate a cost, you get a negative sign. The angle is 2 pi ft. So that means d by dt cos of 2 pi f is equal to that. So that means cos 2 pi ft integral is going to be equal to 2 pi f sine 2 pi ft dt. We cross multiply that one there. So when you interpret this one, you get a cos of 2 pi ft, and then when we integrate, this one is now going to be equal to 2 pi f, the integral of sine 2 pi f dt. So eventually we end up having that sine 2 pi f dt integral is going to be equal to, remember our negative, we're carrying it over. So this one is now going to be equal to, we divide 1 over 2 pi f cos 2 pi f t. In other words, this one is the same as that one. So here in this question here, where there is integral of sine 2 pi ft, we are going to be replacing it by that expression. So we are going to be having, therefore, I dot divided by 2 pi f. So the whole of this one, we are now going to be using cos 2 pi ft. Now, if we divide both sides by v, so we get that v is now going to be equal to we divide by c. So the relationship between that one is going to be that. So this is now going to be the same as v equal to v naught cos of 2 pi ft, where v naught is the same as I naught over 2 pi fc. So you now realizing we began with I naught equal to I naught sine wt. We are now ending with v naught cos wt, but v naught is negative, which implies that this is the same as v naught sine wt, which is 2 pi minus pi over 2. So we conclude that voltage lags current by pi over 2. The voltage lags current by pi over 2. So the question has come, in fact, it's time that it is doing it in a reverse way form. So that is an aspect that we had not concluded the other time. So, the last part of the question were to draw on the same axis the graph showing the variation of voltage across the capacitor and the current against time. Essentially, the graph is the same, which we may redraw. as you have noted. We are drawing a graph such that the voltage line is current by pi over 2. This is the voltage curve. And then this is the current curve. The current I not cos WT. And then cos sine WT. The voltage and current. Then this one is the peak value of the current. That expression is the peak value of the voltage against time. Now, the last question was say, explain the phase relationship between voltage and current. Now you can see initially, when the voltage is 0, current is maximum, or current is leading voltage by pi over 2. So now you need to know that charge Q is equal to Cp. So in our capacitor circuit of this form, that is capacitance C, voltage V, and WT. So when the voltage is increasing, the capacitor charges. That means when the voltage is 0, the charge at the capacitor is 0. So when the voltage increases, as the voltage is increasing, the capacitor starts to charge. In other words, electrons start drifting from one side to another side, such that this one becomes positive and that one becomes what? Negative. Now, when the voltage is increasing, the charge already present on this negative plate starts repelling the incoming electrons. And therefore, when the voltage becomes maximum, there is maximum repulsion for the incoming electrons. And therefore, once that one is reached, current flow becomes 0. So that means at maximum voltage, the current is 0. And when the voltage is decreasing, the current flows, the current increases. And when it reaches maximum, the voltage becomes 0. So therefore, current and voltage are usually out of phase. They are out of phase, meaning that as one is increasing, another one is always going to be decreasing. So that is what the other question intended. So what we want to handle today is power in a capacitor. Power in a capacitor. Power in a capacitor. Average power dissipated in a capacitor. We need to know that power P is given as IV, where I is equal to I naught sine WT, and V is equal to V naught sine WT. So that one implies that power Q now is going to be equal to IV sine I naught V naught sine squared Wt. So therefore, average power is going to be equal to I naught V naught sine Wt, where in a capacitor, the current leads voltage by pi over 2, meaning that the value of current is the cost value. And therefore, the average power is now going to be equal to I naught V naught cos sine Wt cos Wt, which is going to be the same as, if we follow the working, we are now going to be I naught V naught sine Wt cos Wt, which is now going to be the same as the resistor. So we are saying, which is now going to be the same as I naught cos Wt, which is now going to be the same as I naught sine 2 Wt. So average power P is now going to be equal to I naught P naught, the average of sine of a double angle, but sine of a double angle is 0. So therefore, the average power in a capacitor is 0. The average power dissipated in a capacitor is 0. Therefore, we're now going to conclude that power absorbed in a capacitor is 0. And why is it that the power absorbed in a capacitor is 0? Let's analyze the graph of the power generation. In a capacitor, this is voltage. First half cycle, second, third, fourth. We had said that the charge Q is equal to CV. So when the voltage is increasing, the capacitor charges. In the first quarter cycle, when the voltage is increasing, the capacitor charges. In the next quarter cycle, the capacitor discharges. You need to know that energy stored in a capacitor is given by a half CV squared. So that means the energy, if the capacitor charges, the voltage has increased. Energy is stored within the plates of the capacitor. When the capacitor discharges in the second half cycle, the stored energy is returned back to the source. This is the source. The stored energy, in the process of discharging, the energy is returned back to the source. In the next quarter cycle, the voltage increases but in a reverse direction. The capacitor charges, energy is stored in the electric field of the capacitor. So in the fourth quarter cycle, the voltage is decreasing to 0. The capacitor discharges and energy is taken back to the source. So you can now realize that in all the half cycles, energy is stored and then energy is released. So the average energy stored by the capacitor is going to be 0. So that's why our calculation, we have noted that the energy stored in the capacitor is 0. And the explanation is that. Then we want to talk about Sc3 resistor. We said in a resistor, the work is easier and shorter. So in a resistor, from Ohm's law, V is equal to IR, which implies that resistance is just going to be equal to V over R, V over I, and therefore the voltage and current vary the same way. So that one will imply that variation of voltage and current are going to be in phase, which we need to prove. So now you can now say that given that this is a circuit containing a resistor in an alternating circuit, resistor R, voltage V equal to V1, sine WT, providing the current I. So now I'm going to say that instantaneous voltage is that, current I is going to be V over R, which is now going to be V naught over R sine WT. So therefore, the value of current I is going to be equal to V naught over R sine WT, which is of the form I equal to I naught sine WT, implying that peak value of current is now going to be V naught over R. Now you can see the relationship between that value of current you have got and the voltage which we supplied are the same. Therefore, we can now conclude that in a resistor, current I and voltage V are in phase. Are in phase. They vary the same way. Current and voltage, they vary the same way. So graphically, variation of current and voltage is now going to be in this form. If that is the graph for voltage, then this will be the graph for current. So this is now going to be the variation for current, voltage V naught sine WT, and then current I is equal to I naught sine WT. So that's why we say the current and voltage they vary the same way. And how about power in a resistor? Power in a resistor. Power in a circuit concerning the resistor. Power is given by IV. So that's going to be I naught sine WT times V naught sine WT, which is now going to be I naught V naught sine squared WT, and giving us the expression for power. So therefore, average power, we symbolize it by that letter, which is now going to be equal to I naught V naught average of sine WT, where sine squared WT average is equal to a half. So we substitute in here I naught V naught. All this one is a half. So the expression for average power will turn out to that one. But the fact that we know from Ohm's law that V naught is equal to IR, so it will turn out that we can substitute where there is V naught and put there IR, and the expression turns out to be I naught squared R. So this could be an expression for average power. This could also be an expression for average power. A half I V naught or a half. Or you can substitute for current and then put the same resistance. So in our calculation, there's an example that we give concerning average power. So we give you an example. The sinusoidal current I naught is equal to 4.0 sine 2 pi ft, and the value of the ft is 100 T. Now the question, we are required to find the mean power and then deduce the value of the current. So average power, we said, is given by, you can use a half I naught squared R. The resistance, according to the question, the resistance was given as 2 ohms. So you can now substitute in here as a half. The I naught is this one, which is 4 squared, and with the resistance R, which is 2. And then we end up with 16 watts. Or you can use the other alternative of simply say that I naught is that. So you can now simply say that I is equal to 4.0. That average power, sorry, average power is equal to I naught in form of I naught squared R sine WT. And then we can simply say that this is going to be the same as I naught, according to the question, that is going to be 4.0 squared times the resistance, which is 2. The average here is a half. So a half goes and then you get 16 watts. So either way, we try to work it out. It is going to be okay. Now, there are few question answer approaches that are given, but I think those will be handled in our next session. The current I, we could also get it by comparing the square values. So we had left you with an activity, which I want you to try. There is activities involving the following numbers. It is involving number 1, 2, and 3, which I want you to try in our next lesson, those are what we are going to be discussing, inshallah, when we meet again. I now come to the conclusion of the lesson. I thank you so much for learning with me. We'll meet inshallah next week when we have gone through that work, and then we see what to come to. Assalamu alaikum wa rahmatullahi wa barakatuh.